Hello and welcome to our look at factoring polynomials in Math 10C. This is a three-part lesson. We'll check our specific curricular outcome, look at special products and factors, then get into how to actually factor special products. Our curricular outcome. Students will be able to demonstrate an understanding of common factors and trinomial factoring, concretely, pictorially, and symbolically. So, special products and factors. Now, we know if two numbers m and n can be multiplied to make product p, then m and n are considered factors of p. We know this just from numbers. We also saw two special products in our previous lesson. If we take a plus b and square it, we get a squared plus 2ab plus b squared. And we have difference of perfect squares. A plus b times a minus b is a squared minus b squared. How can we apply this to factoring polynomials? Well, if we have, say, 6x squared plus 5x minus 4, we can get that by taking 2x minus 1 times 3x plus 4. So 2x minus 1 and 3x plus 4 are both polynomial factors of the trinomial, tri because there are three terms. They are polynomial factors of the trinomial 6x squared plus 5x minus 4. In general, some polynomials can be factored completely into binomials with integer coefficients, while others cannot be factored with real numbers at all. The number of x-intercepts of a polynomial represents the maximum number of factors which can be extracted. So if ax minus b is a factor, then that polynomial will have an x-intercept at x equals b over a. So if we come to our first examples here, 2x minus 1 is a factor, so this polynomial will have an x-intercept at x equals 1 over 2. It will also have an x-intercept at x equals negative 4 over 3. When completely factored, a polynomial will have a greatest common factor plus binomial polynomials of degree 1. Now, completely factoring in that way may require moving out of the real numbers and including what we call the complex numbers, the square roots of negatives. Those are not a part of Alberta's curriculum. So you won't have to go there, but I like to make sure students are aware of what's coming. So you don't walk away thinking this is the whole story and then have to unlearn that down the road. Little bit of enrichment well beyond Alberta's high school is the fundamental theorem of algebra. If our coefficients are allowed to be complex numbers, so that's combinations of real and imaginary numbers, then the degree of polynomial will be exactly the same as the number of factors. So this quadratic we have with 6x squared, that's degree 2, it would have two factors. We have them. But that would be true of everything. All right, so how do we factor difference of perfect squares? We know when we multiply them, we have a plus b times a minus b, and that factors into a squared minus b squared. But when factoring, we do it backwards. We start with the a squared minus b squared and end with a plus b times a minus b. For example, 16x squared minus 25. Both 16x squared and 25 are perfect squares. So we can take our 16x squared, turn it into 4x by taking the square root. We could take our 25, take the square root of that, we get 5. We've now written this polynomial in the a squared minus b squared form. So now we just copy it over. A is 4x and B is 5. So we'd have, actually I guess to really fit the pattern I have on the line above, I should have written 4x plus 5 and 4x minus 5. Still, they commute. So we could just take our 4x and our 5 and write them in those spots. Another example here, 32x squared minus 50. These are not perfect squares, but they have a common factor of 2. When we pull that 2 out, we are left with 16x squared minus 25. Well, we just solved that example. So this is 2 times 4x minus 5 times 4x plus 5. So we had to pull our common factor out first, but after that we were left with the difference of perfect squares. If we have our product of perfect squares factor, when we're starting with a plus b and square that, we end up with a squared plus 2ab plus b squared. Factoring, again, we go the other way. So if we have 16x squared plus 40x plus 25, we can check if it fits the pattern. We're starting with a 4x squared, so a would be 4x. We end with a 25. That's a perfect square. B would be 5. We ask ourselves, does this fit the pattern? Does that middle term fit the pattern? 2 times 4x times 5, does that make 40? And it does. So we have our pattern, and it turns into 4x plus 5 all squared. Another example. Notice here, it's double the first again. This is an example where we look at this and say, oh, there's a common factor of 2. So we pull that out first. I highly recommend looking for common factors before you factor any polynomial at any level. It will make your life easier if you find one. But once you pull out that factor of 2, it reduces to the previous problem, and we just jump to the 4x plus 5. Right, let's look at some examples. So let's factor 49r squared minus 36. 49r squared and 36 are both perfect squares. They're separated by a minus sign. We have no term with just r. That's a difference of perfect squares. So our a here would be the square root of 49r squared. That's 7r. And b is 6. So 49r squared, we take that square root. And with 36, we take that square root. That's a 6. Fitting this pattern, we put our 7r's and our 6's where they belong. This is now fully factored. Now this one, we're starting and ending with perfect squares. That ending perfect square does not have a negative sign. We have a cross term, as they call it, that linear term in the middle. We have to see, does this fit our a plus b squared pattern? Well, if it does, our a would be x. Our b would have to be 7. And in fact, it's a negative 7. So the square root of 49 can be positive or negative 7. To make this 14x negative, it would have to be the negative 7. So this does fit the pattern. We check, can we find a b squared that makes the 2ab equal to negative 14x? And we have. So this is x minus 7 squared. We're going to factor 18r squared minus 98. Promising start. We have an r squared. We're subtracting. There's no linear term. It's leaning towards difference of perfect squares, but neither of these is a perfect square. They are both even. So if we pull out that common factor of 2, now we have a difference of perfect squares left. So that 9r squared is a 3r all squared. 49 squared is, or the square root of 49 is 7. So this becomes 2 times 3r minus 7 times 3r plus 7. Exercises. Time for you to show what you can do. So let's factor this one. So pause the video, take whatever time you need. All right, now you should have your answer. You've unpaused the video. 36x squared and 121 are both perfect squares. And that cross term does fit the pattern. So 6x plus 11 squared produces this result. Here, factor this one. Pause now, take whatever time you need. I trust that you have unpaused and recognized that this is the difference of perfect squares pattern. And our perfect squares are 5x and 8y. Let's factor this one. Pause, take whatever time you need. If you need a hint, look again for common factors. All right, I trust you've paused, unpaused. You've got your answer. We'll move forward. We have a common factor of 5. And then what we're left with, the 4x squared minus 12x plus 9, fits our product of perfect squares. So that's 2x minus 3. In summary, we can reverse the multiplication of numbers with division or with divisibility rules. We can reverse the multiplication of polynomials with factoring. We will see more advanced factoring as we go forward, including a polynomial version of long division. For those outside Alberta watching the video, 20-1 is our mainstream grade 11 course, 30-1 is mainstream grade 12. Yes, we have interesting naming conventions and numbering conventions. So the predictable patterns of special products can be used to simplify factoring in those particular cases. If you recognize the pattern, you can then jump to the solution. If you have any questions, any feedback, anything you'd like to see expanded on, well, please let me know in the comments. I will do my best to respond in a timely fashion.